Okay, I want to continue on with what we were doing about the acids and bases and how to essentially distinguish between the strong acids and strong bases. And I told you a general concept that if you have an HNO2, which is a nitrous acid, and you compare that to nitric acid, which is HNO3, you can compare the two and you can say that nitrous acid is going to be less acidic as compared to nitric acid. And if you consider bases, on the other hand, in general, if you have a group 1 such as sodium hydroxide, or if you have KOH, which is potassium hydroxide, so group 1 or group 2 hydroxides are in general considered stronger as compared to organic bases, or something like ammonia. So continuing on with that, I want to discuss the conversion of molecular equations into complete ionic equation and net ionic equation. So if your reaction is, let's say, between a strong acid such as HCl and strong base, okay, so it's a strong acid strong base type of a reaction. My acid is HCl and my base is something like sodium hydroxide, NaOH. So hopefully you can envision in this, I have an H plus with a Cl negative, I have an Na plus with an OH negative, and when you do the double replacement reaction and you switch the partners, you're going to get HOH and you'll get NaCl, and those are the two products that I've shown you here. Now, this is a balanced equation and is also your molecular equation, and you can of course convert it into a complete ionic equation by simply converting everything that has AQ by it. You can just simply break that into the corresponding ions, and so HCl will become H plus and Cl negative, NaOH will become Na plus and OH negative, water will remain as is, and NaCl will be Na plus and Cl negative. So Na and Na, sodium and sodium, is going to get cancelled because that's a spectator ion. So would be the Cl and the Cl. What remains is H plus OH negative gives you water. So this last equation that you got is what is called as the net ionic equation. Of course, if you add a molecule of water on both the sides, you can even write it in a more modern method, that hydronium ion, which is this H3O plus hydroxide, gives you 2 moles of water, something we are going to discuss in good detail in general chemistry too. But realize we would be able to utilize and come up with this net ionic equation for strong acid, strong base, because in this case we expect complete ionization of both the acid as well as the base for that matter. How would things be different if instead of having a strong acid, strong base, I had, let's say, a weak acid, strong base, or maybe a strong acid, weak base type of a system? What would happen then? So I'm going to consider, for the purpose of this course, just let's focus on the weak acid, strong base, something similar to HF, which is a weak acid. Even though I have written the letter AQ right by that, the fact that it is a weak acid tells you that this is not going to ionize completely. This is actually the only exception to that rule. And so when you have to convert it into complete ionic equation, you will keep the HF as is. NaOH will be broken into Na plus and OH negative. Water will remain as is, and sodium fluoride will be converted into Na plus and F negative as well. So now the sodium and the sodium will get cancelled off, and what remains is going to be HF plus OH negative, giving you water, and F negative. And so this equation that you get at the end of the day is the net ionic equation. And notice there is a negative charge on the right hand side, there is a negative charge on the left hand side as well. It is a balanced equation. You have 2 hydrogens on the left hand side and you have 2 hydrogens on the left hand side. one oxygen on each side, one fluorine on each side. So it is a balanced equation as well. The question here is, which of the following is not an acid-base neutralization reaction? So recall from our discussion a couple minutes ago that in case of an acid-base neutralization reaction, you're seeking reaction of an acid with a base to give you salt and water. So anywhere where you're getting a salt and water, those will be acid-base neutralization reactions. The last reaction shows you generation of two or starting materials or two aqueous solutions, two clear solutions, which upon mixing with each other generate a solid. So that's the case of a precipitation reaction. Let's write that somewhere. Precipitation reaction. So the correct answer to this question is the last choice. Okay, let's then discuss the redox reactions. What are redox reactions? Now, redox reactions are those that involve a reduction, and ox is from oxidation. So there will be a concurrent set of reactions. For every oxidation, there will be a reduction of the species as well. So one might ask, what are oxidation and reduction reactions, which I'm going to spend some time on. But what I really want you to realize is that the oxidation and the reduction must occur together. They're not going to occur, kind of on their own in an independent manner. If something is going through an oxidation, something else has to undergo a reduction reaction. So for example, if you consider the formation of sodium chloride, you get the NaCl by the formation of Na plus and the formation of Cl negative. Now Na plus is generated if you have let's say sodium. Let me write that somewhere here. If you have sodium, which is the metal, if that loses electron, and if chlorine, Cl2, gains electron, well, for the sake of, if it gains that electron, so I'm going to write that as Cl negative, then you would say that a redox reaction is taking place. Realize loss of electron is oxidation. So the first step we are seeing, that is oxidation, and the second step we are seeing, the chlorine one, that is reduction, and the two will have to occur together for us to be able to call it a redox reaction. Another example that I have here, I have iron metal which reacts with, let's say, copper sulfate, so Cu2 plus, and what you get is Fe2 plus and copper. Realize what's happening to iron. It's losing electrons. What's happening to copper? It's gaining those electrons and deposit the copper metal. So realize that again, what lost electrons, that's oxidation. What gains electrons, that goes through reduction. So one thing hopefully that you can see is that oxidation is loss of electrons, and you can remember that perhaps by mnemonic, general mnemonic, Leo the lion says grr. Loss of electron is oxidation, gain of electron is reduction. So let's write that as well somewhere. Reduction is gain of electrons. And if you can remember that, you will be in a pretty happy boat throughout any form of chemistry. So realize in this reaction where I have Fe plus copper 2 plus giving you Fe2 plus and copper. Notice iron has given you Fe2 plus, and that means the electrons have been lost, and so it's an oxidation that has occurred, and you would say that iron 0 in this case is going to be acting as a reducing agent. That means It itself goes through oxidation, but it reduces other materials around it, and hence you would call it a reducing agent. So reducing agent can be defined as a species that can lose electrons, go through oxidation, but it's going to facilitate reduction of other species. Itself goes through oxidation. So these kind of species usually will be electron rich. So metals are good, neutral atoms are good candidates for this because they can easily lose electrons. Also realize Cu2 plus is what goes through reduction. So we are going to call the Cu2 plus an oxidizing agent, and an oxidizing agent is going to be a species that can gain electrons and facilitate oxidation of another species. So these in general are going to be electron deficient. They will have a greater amount of charge to begin with. Another way to look at it is that you would find the oxidizing agent more on the right side of the periodic table. So things like chlorine, oxygen, fluorine, these are good oxidizing agent. On the other hand, reducing agents you'll probably find more on the left side of the periodic table. So better metals are good reducing agents as well, whereas better non-metals are going to behave as good oxidizing agents. Now the question here is, which is a reduction half reaction? And I have given you 4 choices. Recall Leo and Gur. Leo the lion says Gur. So loss of electron is oxidation, gain of electron is reduction. Another one that you can use, but I don't personally like that a lot, it's oil rig. Oil rig, which is oxidation. So this stands for oxidation. Oxidation is loss of electron. The only problem that I have with this one is you have to kind of remember that the loss is for the electron, and there's more than one ways that you can define oxidation and reduction, and if you mess that up then you will go in circles before, it'll be very easy to do that. Reduction is gain of electron, but if you can remember that, I'm okay, whatever works for you. Again, realize I'm calling that a reduction half reaction because reduction plus oxidation together makes up the full redox. So if you look at the first one, that is causing a loss of electron, loss of 2 electrons rather. The second one is loss of 1 electron. The third one is loss of 3 electrons. And we have the last one where 1 electron is being gained. So the reduction half reaction is going to be the last one in this case, which is gain of electrons. Now, the next question asks you, for each of the following, identify which species is the reducing agent and which is the oxidizing agent. So right here we have calcium plus 2H plus giving you Ca2 plus and H2. The best way to go about it is to identify what goes through oxidation, what goes through reduction. So you have calcium at 0 and it is becoming plus 2. You have it at 0, it's becoming plus 2. That's an increase in oxidation number, and that would have occurred by the loss of electrons. That means calcium to Ca2 plus is going to be oxidation. So this is going to be oxidation. You have H plus, it became H2. That means you're going from plus 1 to 0. That's a decrease in oxidation number, and that would mean that H plus is going through reduction as the process. So whatever undergoes oxidation is going to be called as a reducing agent, and that means a metal is a reducing agent. Whatever undergoes reduction is going to be going through an oxidation. It's going to be called as an oxidizing agent, and in this case it's a non-metal, so that makes sense as well. So hopefully you can see another way to identify oxidation and reduction is that increase in positive charge, positive charge, positive charge.